we want to go over some important rotational quantities like kinetic energy, inertia, and Newton's second law for rotation. Let's start with kinetic energy. Let's say we have 4 point masses, M1, M2, M3, and M4, connected with massless rods. So the only mass we have to worry about are these point masses. M1 is a distance R1 from the axis of rotation. This is the axis of rotation. And these rods are massless. As are the other two. So if this is rotating, we've got 4 masses that are moving. And when mass moves, we know it has kinetic energy. And how much kinetic energy does it have? So the kinetic energy of this system, I'm just going to put a sub R there, the rotational kinetic energy, that's just equal to the kinetic energy of each of the masses as if they were moving in a straight line. Kinetic energy of 1 plus 2 plus 3 plus the kinetic energy of particle 4. We'll just find the kinetic energy of each one and add it up, and that'll be the kinetic energy of this rotating system. For particle 1, it's going to be its mass times its velocity squared. And the same is true for the other masses. But there's a relationship between V and omega. These 4 masses are being held together as a rigid body. As they rotate, every point on a rigid body has the same omega. Their tangential velocities are different based on how far away they are from the axis of rotation. But omega is all the same. So I can substitute in here mass 1 times its velocity squared, which is going to be its radius squared, times omega squared. I don't have to put a sub 1 for omega because omega is the same for all 4. Since omega is the same for all of them, I can factor it out. And the 1/2 is the same for all of them. And I can just write this as a sum. This is the sum of mr squared. And now I compare this to what I typically get for kinetic energy. Normally, I would say my kinetic energy is 1/2 mv squared. M depends on my object, and v is what it's doing, right? Its velocity. So now I've got my rotational kinetic energy into the same form. I've got a 1/2. I've got something that depends on what it's doing, its rotational velocity now. And I've got something here that depends on my object, the mass and how it's distributed about the axis of rotation. For translational kinetic energy, we use 1/2 times the inertia, m, times the speed squared. For rotational kinetic energy, we have a 1/2. We have something that must be the rotational counterpart to inertia here, sum of mr squared. And we have omega squared, the rotational counterpart to velocity squared. So we're going to say that for point masses, I, or rotational inertia. Some people call it moment of inertia. The moment of inertia, the rotational inertia for point masses is just mr squared. And for multiple point masses, we add them up. I is equal to mr squared for a point mass. If there are multiple point masses, we just add them up, just like we do for mass. If you're pulling your wagon and you want to know how much mass is in there, you just add up all the individual masses of all the objects in your wagon and you get the total mass. Same thing here. You find out the rotational inertia for each object that makes up your system, and then you add them up. And if we have a solid object, this summation turns into an integral. So we started with kinetic energy, and we found the rotational kinetic energy was 1/2 I omega squared. And we know I, our rotational inertia, has these different forms for a point mass or for a solid object. We want to figure out Newton's second law for rotation. We know that F is equal to ma, and we know that torque is R cross F. So if we plug that in here, this is the perpendicular acceleration. I'll call it tangential acceleration. Now we know there's a relationship between the tangential acceleration and alpha, the angular acceleration. And I can substitute that in. For the tangential acceleration, I've got r times m times r alpha. So for one point mass, the torque is mr squared alpha. If there are multiple, I would add them up. And we get Newton's second law for rotation. The net torque is the rotational inertia times the rotational acceleration. The net torque is I alpha. So just to summarize, we found our rotational inertia, and that has a different form depending on whether we're talking about a point mass or a solid object, but it stems from the same equation. The mass times the square of the distance from that mass to the axis of rotation. If there's more than one mass, you add them up. If there are lots and lots of little masses, like we have with the solid object, we integrate. And our kinetic energy, 1/2 I omega squared for a rotating object. And Newton's second law, sum of the torque is I alpha.